In my previous video, I have derived one-dimensional wave equation which gives displacement of a stress string in case of transverse vibrations. So we will find solution of this one-dimensional wave equation here. So you know that one-dimensional wave equation is dou square y by dou t square is equal to c square dou square y by dou x square, where c square is t by m. So same equation can also be written in the form dou square y by dou x square is equal to 1 by c square into dou square y by dou t square. So now we use method of separation of variables to solve this partial differential equation. Now in this case, y is the dependent variable and x and t are independent variables. So therefore, we assume y is equal to xt is a solution of the first wave equation. Here x is a function in x alone and t is a function in t alone. Now the first equation contains two partial derivatives, that is dou square y by dou x square and dou square y by dou t square. So we will find out these two derivatives from second equation. So now the second equation is y is xt. So now first we find dou y by dou x, and here t is a constant with respect to x, therefore dou y by dou x is t into dou x by dou x. But here this capital X is a function of small letter x alone, so we can write this as t multiplied by dx by dx. These two will be same because capital X contains only one variable, that is small letter x. So therefore this is our dou y by dou x, and now dou square y by dou x square is equal to then t into derivative of this term, that is d square x by dx square. So we got one derivative which is there in the first equation. Similarly, we can find dou square y by dou t square as x multiplied by d square t by dt square. Now we substitute these two derivatives in first equation and then we will separate the variables. So here after substituting we will get it as t d square x by dx square is 1 by c square multiplied by x d square t by dt square. Now we take all the functions in x to the left hand side and all the functions in t to the right hand side, so that we can write it as 1 by x into d square x by dx square is equal to 1 by c square into 1 by t into d square t by dt square. Now then we will equate each side of this equation to a common constant k, so that we get two equations, that is 1 by x d square x by dx square is k and 1 by c square t d square t by dt square is equal to k. And now we can see that both are second order ordinary differential equations. So now we can use any method for solving these two ordinary differential equations. So now we can rearrange terms of these two equations again, so that we will reach in two equations which are named here as 3 and 4. So that we have two equations now, that is d square x by dx square minus kx is 0 and d square t by dt square minus kc square t equal to 0. Now we can see that both are linear equations of second order with constant coefficients. And here the right hand side is 0. Therefore, complementary function will of these two equations will give solutions for these two. So first of all, we will write down auxiliary equation and then find complementary function. And before doing that, we can see that the value of the complementary function depends on the value of the constant k. This k is known as separation constant and it can take either negative value, 0 or positive value. So we will consider these three cases separately here. So therefore the first case I take it as k as a negative value. So then since k is negative, so we will take it as p square. So we can take, its meaning is that we are taking k as negative p square. So that k will be negative. And now substitute the value of k in third and fourth equation so that we will get d square x by dx square plus p square x is 0, d square t by dt square plus p square c square t equal to 0. Now we proceed with writing auxiliary equations. For the first equation, auxiliary equation is m square plus p square is 0. So that m is plus or minus ip and therefore solution of this equation is x is c1 cos px plus c2 sin px. The reason is that the roots of auxiliary equations are complex. So therefore this is the form of the solution. And now you consider this equation, second one. And here the auxiliary equation is m square plus p square c square is 0. Again m is plus or minus ICP complex roots. Therefore t, solution of this equation will be t equal to c3, one constant, cos cpt plus c4 sin cpt. Therefore we can write down the solution of our wave equation. Our assumption was y is xt is the solution. Now we got x and t. Therefore y is c1 cos px plus c2 sin px multiplied by c3 cos cpt plus c4 sin cpt. So this is the solution when the separation constant k is negative. Now consider the second case. So I'll take the separation constant k as 0 so that these two terms will vanish. So the differential equation will be d square x by dx square equal to 0 and d square t by dt square is equal to 0. That is written here. So now for finding the solution, you simply integrate these two equations. So first you consider this one. Integrating, we get dx by dx, that is a constant, I take it as c1, and then x, again integrate c1x plus c2. Now consider the second one. So then integrating dt by dt is a constant, take it as c3, and then again integrating t is c3t plus c4, another constant. So we got x and t, and again y equal to xt is the solution. Therefore substitute x and t. So we got c1 plus c2x multiplied by c3 plus c4t as the solution of wave equation when k is 0. Now consider the third case. K is positive, say p square. That means we are taking k equal to p square. Then the differential equation is d square, okay, this is d square x by dx square minus p square x equal to 0, and second one is d square t by dt square minus c square p square t equal to 0. Now consider the first one. So now this is a linear equation with constant coefficients. So we have written the auxiliary equation, that is m square minus p square is 0. So m square is p square. So we get m equal to plus or minus p. Here values of m are real and distinct. Therefore the solution is x equal to c1 e to the power px plus c2 e to the power minus px. Here c1, c2 are constants. Now we consider the second equation. Here the auxiliary equation is m square minus c square p square equal to 0. Therefore, m square is c square p square, m is plus or minus cp. Again, roots are real and distinct. Therefore, solution is t is c3 e to the power cpt plus c4 e to the power minus cpt. Hence, the solution is y is the product of this x and t. So, we get one more equation. So, we got 3 solutions now that for the wave equation in 3 different cases. But here we are discussing the problem of vibrations. Therefore, the displacement y of xt must contain periodic functions of t. Therefore, from these 3 solutions, we choose only one solution as the possible solution which contains cos and sine terms. Therefore, the possible solution of wave equation is y of xt is c1 cos px plus c2 sin px multiplied by c3 cos cpt plus c4 sin cpt. We will make use of this formula in solving problems.